Hello everyone, in this video we're going to be touching the theme of alternating series. An alternating series is a series whose terms are alternating between positive and negative. And we gotta be very careful here because we're just jumping from positive numbers to negative numbers. We cannot jump between two different things, it's just positive and negative. That's what we call alternating series here. So if we have a series from n equals 1 to infinity of the form an, sum of an, then the n term of the alternating series is, or the n term of the sequence of the alternating series is going to have the form an equals minus 1 to the n, or to the n plus 1 times bn, where bn is going to be another sequence of positive numbers. So to give an example of that, let's check this alternating series here. We go with 1, then we jump to minus 1/2, then we jump to positive 1/3, then we jump to minus 1/4, plus 1/5, minus 1/6. In general, this is just a series from n equals 1 to infinity of minus 1 power to the n minus 1 times 1/n. And if you plug from n equals 1, then you can see that it matches all these different numbers. Now, of course, because we're doing series, we want to know where a series is going to be convergent. So we have a series of the form minus 1 to the n minus 1, or minus 1 to the n, or minus 1 to the n plus 1 power bn times bn that satisfy the condition of being decreasing, and also from having that the limit when n goes to infinity of the sequence bn is 0, then we can say that the series is convergent. We call this the alternating series test. Notice that I'm writing here bn plus 1 less than bn for all n, and this means that the sequence is decreasing. So let's see some examples of that to test convergency or divergency of certain series where they all are going to be alternating series. So first and anything, we have this series from n equals 1 to infinity of minus 1 to the n over n squared. Now the first condition that we want to consider is, well, is this series 1 over n squared going to be decreasing? And there's another way of checking that a series is decreasing than what we usually do. For the integral criteria, I consider this being f of n 1 over n squared, and then I do, well, this is the same that n to the minus 2, and then f prime is going to be minus 2n to the minus 3, and this is negative. So if I first derivative test, f is going to be decreasing. That is normally what we can do, and this is fine. This is one good way to showcase that indeed bn plus 1 is less than bn for all n. It's also very easy to see that limit when n goes to infinity of 1 over n squared is equal to 0. So by alternating series test, we have that this series from n equals 1 to infinity minus 1 to the n over n squared converges. And that's normally what it happens with the alternating series. Okay, but we also can have the case where we can just prove that something is decreasing by just showcasing the inequality. So here we have in the second case minus 1 to the n plus 1 over n. Clearly the sequence here is 1 over n. And then notice that I can just prove essentially, well, n plus 1 is bigger than n. So 1 over n plus 1 is just going to be less than 1 over n. And so this means that bn plus 1 is less than bn. And this is going to happen for all n in the natural numbers. So this means bn is decreasing. So what method to use, it doesn't matter, it's up to you. The one that you feel more comfortable using is the one that you should use. Also, we clearly have here that the limit when n goes to infinity of 1 over n is 0, so this implies by alternating series tests that this converges. Notice that this is alternating harmonic series, and the alternating harmonic series is being converged as opposed as the normal harmonic series that is not convergent. Okay, so the alternated does. Let's see one more case here. We have a series when n equals 1 to infinity of minus 1 to the n over e to the n. Now, in the same case, or in the same way that we did before, we can establish that Bn is 1 over e to the n, or this is e to the minus n. And we can check first very quickly and very easily that this is going to 0. So the next step is always checking that this is going to be decreasing. Depending on the type of function or the type of sequence, one method can be much more easier than the other one. Which one? Well, it depends. It's up to you to show it. For example, with an exponential, I think it's going to be difficult to show an inequality, so I rather prefer go with f of n equals e to the minus n, and then f prime of n being minus e to the minus n. This being negative implies that f is decreasing, and then that implies that Bn is decreasing. And then again, by alternating series test, then this series here is going to be convergent. So again, what to use depend up to your liking. Some ways of proving that something is decreasing much more easier than others. But at the end of the day, you just want to prove that those two conditions holds for alternating series. Now here we have minus 1 to the n times n over n squared plus 1. And so, for example, for this type of function, it's very hard to try to prove that this is decreasing by using a direct comparison. We can certainly check that the limit is 0, since the bottom is has a higher power than the numerator, and so this is very quickly something that we can establish in that way. But if we do the function, we're likely going to much more easier find out that it's going to be decreasing by doing the first derivative test. In this case, this is 1 times n squared plus 1 minus n times 2n over n squared plus 1 squared. And so simplifying this, this is just minus 2n squared plus 1n squared. So this is going to be 1 minus n squared over n squared plus 1, which this is evidently negative as n becomes larger. And then we can say that f equals to Bn is decreasing. And notice that we always had to do this 2 steps. We gotta state this and we gotta state this. If we don't do that, then we cannot claim that by alternating series tests, the series is convergent. So you wanna be very careful when you're trying to make exercises and when you need to establish conditions, because you need to prove that those 2 things happen to be able to use it. Now, let's take a look at one last example. This is a series from n equals 0 to infinity, minus 1 to the n plus 1 over n. And so notice that at glance, this might look like it's in an alternating series, but it really isn't, because this is saying minus 1 to the n plus 1. And so notice that when n is positive, when n is even, then this becomes 1, and then this becomes 2. But when n is odd, then this is going to become -1, and then this is 0. So for example, with 0, plugging 0, well, we cannot plug 0 actually. This is a typo here. This gotta start from 1, because we cannot plug 0 on the bottom. So there's a typo here, gotta start from 1. So at the start, this is gonna start at 0. So 0 plus 1. And then in n equals 2, this is 2 over 2. Plus in n equals 3, this is gonna be 0 over 3. Then in n equals 4, this is going to be again 2 over 4. And in n equals 5, then becomes 0 over 5. N equals 6, then again 2 over 6. So notice that I can kind of transform this series really into a different thing. So now I'm gonna go and write this as the series from n equals 1 to infinity. And notice that this only goes with the odd. So instead of n, I'm gonna be writing 2n. And on the top is always 2. So really, this series in disguise is just the series of 1 over n. And as we know, this series diverges. So this is not even an alternating series case. We don't get the numbers to alternate. It's not an alternating series. And at the end, we see that this series can be really rewritten as the harmonic series. Notice that this is now here, the way that I'm writing this is going to jump only between this and this and this. And it doesn't make sense to do it otherwise, because all the other terms are just 0. So this form, this series here, is just a rearrangement of this series here. Now let's transition to finding out the sums for alternating series. So if we're using the alternating series test, and we're assuming that we have a series for an n equals 1 to infinity of a series -1 to the n bn, and that series is convergent, and we have a sum s, then of course, because we already assume the conditions of the alternating series test, we have that the sequence of the series is decreasing, and the limit goes to 0. So now we can assume then the remainder of the partial sum versus the total sum is going to be less than the n plus 1 term. And this is just a consequence of the nature of the alternating series, plus the fact that there is constantly a decreasing function. Okay, so to just make an example of that, let's find the sum of the series -1 to the n over n factorial with an error of up to 3 decimal places. So first thing, let's double check that this actually converges by the alternating series test. Notice that, of course, n plus 1 factorial is bigger than n factorial. And so we have that 1 over n plus 1 factorial is less than 1 over n factorial. And so we're going to have that bn plus 1 is less than bn for all n. And then we have that as decreasing. So in this case, because it's a factorial and it's not a function that we can take derivative, then it's much more easier to do it by the inequality. Now also, it's very easy to see as well that the limit when n goes to infinity of 1 over n factorial is just going to be 0. So by the alternating series test, we know that the series here converges. We know that n equals 1 to infinity of -1 to the n over n factorial converges. Now, of course, you got to remember that the sum is 1 over 0 factorial plus 1 over 1 factorial, right? 1 over 2 factorial, so on and so on. Okay, and so this is going to be equals to 1 minus, sorry, I forgot the alternating here part. This is minus this plus this, and then let me showcase one number more. Then minus 1 over 3 factorial. So this is 1 minus 1 plus 1/2 minus 1 over 6. And I can go a couple more numbers. And this is like 1 over 24 minus 120 minus 1 over 120, so on and so forth. So now if I check what is, let's say, the B7, the seventh term of the sequence, this is going to be 1 over 5040, and this is like less than 1 over 5000, right, which is approximately like 0.002. And now the sum up to 6 is just 1 minus 1 plus 1/2 minus 1 over 6 plus 1 over 24 minus 1 over 120 plus 1 over 720, which when I add that with the calculator, this is like 0.368. So it's a very small number itself. So if I consider what the partial sum minus, let's say, a term like s of 6 is going to be, then I'm going to have that this is going to be less than b of 7. And this at the same time is going to be less than 0.002. So this is an error of less than 0.02%, 0.0002. And it's not going to affect the third decimal place. So we have this correct up to 3 decimal places, because notice that this factor is not going to affect really this one. Okay. So with that, we can find out that this is an error good enough up to 3 decimal places. If you want to do the same thing for another type of series, you might want to look for something that it produces a similar kind of numbers, so you can figure out what n is going to produce this type of number precisely.